So one day, Edwin Hubble discovered that the universe was expanding, so they named a telescope after him. Well, yeah, there's more to the story. Now imagine a fruitcake baking in the oven. As this cake is rising, the raisins inside are moving farther apart. Something similar happens when the universe expands. But instead of raisins, there are galaxies, which start to spread out. That's why if you randomly pick any two galaxies, the chances are they're moving away from each other. But then the question is, if galaxies are moving apart, why are there still galactic collisions? You see, even while expanding, the universe still remains a playground for galaxies to interact with one another, and they mostly do it by using gravity. All galaxies out there attract other galaxies, and their mutual pull slows down the speed of them moving apart. And naturally, the closer two galaxies are to each other, the stronger their mutual gravitational pull is. On a large scale, it doesn't seem to make any difference, since every galaxy experiences a similar pull in every direction. But locally, gravity kinda overwhelms this powerful cosmic expansion and pulls together two or more galaxies which were initially moving apart. That's how galaxy collisions occur. Plus, some galaxy groups, like the Virgo cluster, aren't expanding at the moment, since local gravity has stopped the expansion process in that region. Some large galaxies can attract smaller ones, and then the gravity of the larger galaxy starts pulling a smaller one toward it. Eventually, it leads to a collision. Galaxies are made up of stars, rock, dust, gas, and other materials. When two galaxies collide, their gases begin to interact. These gases usually exist in large clouds spread throughout galaxy systems. Because of their size, large clouds of gases are more likely to run into large clouds of gases. Then they start getting denser and experience more pressure. Or the combination of gases can cause waves, and the gases can collapse on themselves. Both of these processes lead to the formation of new stars. If two colliding galaxies are of the same size, many new stars are likely to form, making the galaxies shine even brighter. But if the speed of these two galaxies is too high, the newly formed stars can go right out after they appear in the sky. As two galaxies start coming closer to each other, they begin to stretch and deform, creating arms or tails. As a result, an elliptical galaxy can form, or the collision can form a new supergalaxy. In this case, stars from each galaxy will have to find a new place within this gigantic space formation. But of course, there are tons of galaxies that have never collided with others. That's because galaxies are actually relatively small targets in our gigantic universe. They form groups of small clusters where dozens, hundreds, or even thousands of galaxies gather together. Gravity holds them tight together, just like the solar system stays together thanks to the sun's gravity. Galaxies roam within these groups and clusters in a disorganized way. Naturally, collisions are bound to occur, but since galaxies are tiny compared to all that space they live in, massive mergers don't happen often. I'm talking about those collisions between equal-sized galaxies that shake things up on a grand scale. Of all the environments galaxies can live in, the most dangerous place is a group. Because solitary galaxies, living out in the field, seldom cross paths with others. As for galaxy clusters, they are indeed crowded. But galaxies in them move at such breakneck speeds that even if two of them meet, they'll simply race past each other without any dramatic consequences. But groups of galaxies are a different story. There, galaxies move comparatively unhurriedly. It makes it more likely that two galaxies in a group will not only come close to each other, but also get caught in their mutual gravitational pull for a prolonged time. And what will happen if two galaxies come close enough to collide? Well, the best way you can imagine such events is by thinking of them as merges rather than collisions. Galaxies are very spacious, and it's more likely that the stars they contain will just pass by each other. Let's talk about a galactic collision that, according to astronomers, is going to happen in several billion years or so. And our home Milky Way galaxy is going to take part in this space event. But don't worry, we still have some time to brace for the impact. Interestingly, there might be not one, but two collisions, and the first one might happen around 2 billion years from now, when the Milky Way will collide with the Large Magellanic Cloud. This spiral of stars and dust is floating in space about 160,000 light-years away from our galaxy. And although right now this distance is totally safe and you have nothing to worry about, in approximately 2 billion years, the two celestial bodies are likely to collide. And what a view it's going to be! Imagine the Milky Way nearing the smaller galaxy. The supermassive black hole residing in the center of our galaxy will wake up and start gobbling up the stars and gas clouds of the Large Magellanic Cloud with enthusiasm. Thanks to this new food source, the hole will grow way bigger than it is now. It might even turn into a quasar, one of the brightest things you can find in the universe. Our newly awakened black hole will also be emitting long jets of super bright radiation. But people on Earth won't have anything to worry about. These jets won't reach our solar system, and even if powerful gravitational interactions triggered by the merger could probably fling us out into intergalactic space, the chances of this happening are slim. Like me winning the lottery. Stars are located too far away from one another, and even such a catastrophic galactic smash-up isn't likely to jostle our solar system. Now, if our black hole does turn into a quasar, it'll be an even more breathtaking view. The thing about these celestial bodies is that their light can be up to 10,000 times brighter than the light coming from the whole Milky Way galaxy. That's why Earth's night sky might change beyond recognition. The newly born quasar will get rid of some stars and send others flying billions of miles away from their orbits. As a result, all the constellations, as we know them, will disappear from the sky after the familiar stars get too far away for us to see them with the unaided eye. Luckily, the chances that the Sun will get knocked out of the Milky Way are really infinitesimal. But how about the predicted collision with the Andromeda Galaxy? Will our solar system survive this catastrophe as well? Right now, the Andromeda Galaxy is nearing the Milky Way at a speed of 68 miles per second. As you may guess, it's very hard to figure out its actual speed. And until 2012, researchers weren't even sure if the collision was going to happen or not. Unfortunately, it turned out that we had to prepare for the appearance of Milkdromeda, or Milkomeda, a structurally new galaxy consisting of the merged Andromeda and the Milky Way. Now, on the other hand, such collisions aren't something out of the ordinary if you consider galaxies' lifespans. Besides, even though the Milky Way is home to more than 100 billion stars, and the Andromeda Galaxy contains about 1 trillion, the chances of several stars colliding during the galaxy's merge is really low. The reason is the same: stars are located too far away from one another. For instance, the closest to our Sun star, Proxima Centauri, is more than 4.2 light-years away, which is about 30 million diameters of our Sun. In simpler terms, if the Sun was the size of a ping-pong ball, Proxima Centauri would be the size of a pea located 680 miles away, and the entire Milky Way would be 19 million miles wide. Wow! As for other stars, can you imagine ping-pong balls hanging in space every 2 miles? Great! Now you have a miniature model of our galaxy. Now, when we say the word universe, we're already picturing this vast space filled with stars, planets, and comets. Truth is, most of us find it hard to actually picture how large the universe is. Well, try to think of space as the biggest playground you've ever seen. Right now, our space playground goes on for 46 billion light-years. It wasn't always like that. On that note, you've surely heard of the Big Bang Theory. Let's try to unpack it. Imagine the whole wide universe, every star, planet, down to the smallest particle, squished into a tiny super-hot ball the size of, let's say, an apple. From that point on, we've got a pretty neat roadmap of how things unfolded in the cosmos. Dive even deeper into the universe's past, and things start to get a bit blurry. The energies and temperatures rise, and suddenly, our rulebook of physics doesn't make sense anymore. When we reach these early times, gravity, that force that keeps our feet on the ground, starts acting all mysterious. This is where we bump into the great puzzle of our time, quantum gravity. And here's the honest truth, we've still got some homework to do on that one. What made the Big Bang go pop in the first place? Well, it's kind of like asking what happened before the first page of a book. There's no page zero, or at least that's the answer that quantum physics provides. It tells us that there are events in the universe that just, happen. It's not because we're not looking where we should, it's just how the universe works. Or at least, that's our current understanding of it. Right after the blast, everything was just a bubbly mix of gas, like this soda can that just got opened. This gas, which was mainly helium and hydrogen, began to stretch out and cool down. If we could time travel to those times, we'd see a younger, hotter, and cozier universe. Cool telescopes like the Hubble and James Webb let us peek into those ancient times. And what we see is fascinating. Earlier galaxies were like the cute photos of the universe when it was younger, tinier, less heavy, and not as evolved as they are now. Over billions of years, the universe stretched out like a soap bubble. Imagine countless shiny marbles inside it, representing stars and galaxies. As the bubble grew bigger, the marbles spread out. Today, inside our bubble, we have trillions of galaxies. For every single galaxy we can spot, there are tons more we haven't seen yet. Some are too tiny, others are too far away. We still can't see them even if we use the fanciest telescopes available. Just to paint you a better picture, know that today our very own Milky Way is home to around 400 billion stars, similar to the Sun. It was a lot different in the past, though. Our galaxy began its journey like a little bundle of stuff, just a tad denser than most things in space. A lot of it was actually made of dark matter. Our closest star friend, named Proxima Centauri, is 4.2 light-years away. To put that in earthly terms, that's like taking a road trip around our planet millions of times. It's also about the same age as the Sun. If we could have looked at the exact spot about 5 billion years ago, it wouldn't have been there at all. Many stars live together in groups, kind of like families. However, most are solo adventurers, experiencing the vastness on their own. When you zoom out from our Milky Way and peek into the larger universe, it's more, empty, like a vast piece of countryside between big cities. In our cosmic area, we've got some cool neighbors. The Andromeda Galaxy, for instance, is just a stroll away, in cosmic terms, at 2.5 million light-years. And there are lots of smaller galaxies too, like the Triangulum Galaxy and the Large Magellanic Cloud. Our local hangout spot, which includes all these galaxies, spans about 3 million light-years. As we explore further, galaxies seem to gather in clusters, like suburbs. Connecting these clusters are threads of galaxies, creating a giant web in the universe. Galaxies are clustered this way because, just like magnets, they love to pull stuff towards them. If we could turn back time, we'd see a different picture. That's because throughout history, the popular galaxies with lots of stuff became even bigger, while the less popular ones gave their items away. From Earth, we can only see objects that are 46 billion light-years away at the most. If we put all this space into a giant box, its volume would be unimaginably huge. The main reason our universe is such a grand spectacle today is that it's been growing nonstop. Every year, its size increases a little more. In fact, the universe is expanding faster than the speed of light. Sure, we can't feel it down here on Earth, but there are clear signs in the universe that it's happening. We're still not sure why the universe behaves like that, but scientists are working hard to figure out this mysterious expansion. Our understanding of the universe has changed a lot over the years, too. Back in the day, when our world had more trees than buildings, people from all corners of the Earth would gaze up at a twinkling sky above. For many, the sky was their roadmap, alarm clock, and spiritual connection point. Now, imagine not having a smartphone or a compass, and still being able to find your way home or knowing when to plant your crops. That's because our ancestors had the sky. They knew when it was time to take care of plants, navigate ships, or celebrate special occasions, all by watching the stars and planets. Long ago, people in Babylon spotted some stars that behaved a little weirdly. These stars seemed to have a mind of their own. Obviously, we know now that they weren't stars at all. They were planets, like Venus and Mars, that sometimes wink at us down here. There was also a time when we believed the Earth was flat. Well, at least some people did, before Greeks in the 6th century BCE figured out that it's round. They even managed to guess its size by watching shadows in different places. They were pretty close with their estimations, especially if you take into consideration their limited tools. Now, speaking of our planet, there was also a time when humankind believed the Earth to be the center of the universe. We also believed everything else was just spinning around it. That was until a man named Copernicus did a bit of research and figured out it was actually the sun coordinating all the movement in our system. And soon after, other thinkers and stargazers joined in on the fun, changing how we perceive the universe using new tools. Speaking of tools, thanks to a telescope, Galileo found out that Jupiter had massive moons tagging along. We call them the Galilean moons today in his honor. But the universe kept tossing surprises our way. Some people started cataloging stars, clusters, and nebula, while others found mysterious rays that our eyes can't see. And just when we thought we had it all figured out, Edwin Hubble, not the telescope but the man behind the name, discovered something amazing too. He realized that other galaxies are in fact moving further away from us. These days, we're looking at the universe in a different way. We know how the timeline works now. We know that our time here on Earth is limited. No wonder astronomers are eagerly scouting through the vastness of space, looking for planets similar to ours. There is no other planet that can safely accommodate us in our solar system. But we can use our neighboring planets and satellites for scientific purposes. Take Mars, for instance. In the following decades, NASA is planning to send all sorts of devices and even people up there. If the experiment proves to be successful, we might end up living there for a while, or at least use it as a pit stop for our next exciting destination. Legend has it that in the 17th century, Sir Isaac Newton noticed an apple fall from a tree and began wondering why the fruit had fallen to the ground and not upward or sideways. Well, that would be freaky. After years of studying, he concluded that gravity must be the culprit. The scientist called it a force of attraction that existed between all objects. But it was Albert Einstein, many years later, that revolutionized these ideas about gravity. Legend also has it that he wasn't completely satisfied with Newton's findings. Something just didn't seem right. As a young scientist, Einstein had some trouble formulating his theories, trying to explain the behavior of moving objects. When an experiment came to his mind, he called it the happiest of thoughts. Gravity feels like the sensation of riding in an ascending elevator. He called it general relativity. Einstein began working tirelessly, trying to prove this idea. At one point, he even complained he was on the brink of losing his mind. Now, in the simplest terms, general relativity claims that gravity is the curvature or warping of space. The greater mass an object has, the more it warps the space around it. Imagine a heavy ball resting on a trampoline. The rubber sheet under it gets warped under its weight. It's the same with our sun. It's big enough to twist space across the entire solar system. That's why our planet, as well as all the others, orbit around the star. This warping also impacts how we measure time. If you look at your watch, time seems to go by at the same rate every day. But if you hike to the top of a mountain and your friend wanders through a valley at the bottom of this mountain, you'll see that your watches will calculate time differently. One watch will tick faster, while the hands of the second one, which is traveling through the valley, will move more slowly. That's because gravity affects how fast time goes by. With these experiments in mind, Einstein concluded that gravity was not a force of attraction, but rather a curvature in the fabric of space-time. We feel gravity as a force simply because we're placed on some surface. If there was no surface and no attraction between us and this surface, we would become weightless. If you don't mind getting some weird looks, try this experiment. You'll need a bathroom scale and an elevator to ride. You'll soon see that your weight fluctuates as you move up and down in the building in the elevator. The gravitational force is the same, but your weight is different because the elevator speeds up and slows down. Aboard the International Space Station, astronauts literally move along with the station, so there's nothing to push them against the side of the station so that they have some weight. Even if we still think of gravity as a force, it's the weakest one we know. First of all, it only attracts. There's no negative counterpart that could push things away. And weirdly, even though this force is strong enough to keep galaxies together, we still overcome it every day. Every time you lift an object off the floor, you overcome the force of gravity produced by the entire Earth. Ooh! Just to paint a better picture, Earth's gravitational pull is weaker than the power of a refrigerator magnet. The fact that our planet has gravity also affects the way we look and act. All creatures on Earth are limited in growth by the height of their skeleton and by how much weight it can carry, which is directly proportional to gravity. That's why some marine creatures can grow bigger. The largest animal on our planet right now is the Antarctic blue whale. It's about the size of 2 school buses combined. That's because sea creatures can float, which slightly counteracts gravity. The effects of gravity can be seen in people, too. We are taller in the morning than we are in the evening. Our everyday activities and the added effect of gravity make the cartilage in our ankles, knees, hips, back, and neck compress. Once you have overnight rest, the cartilage swells back to normal. Gravity might also affect your shower routine. That is, if you're an astronaut. They have to rely on the old-fashioned way of bathing up there on the space station. They can't take a shower since the force of gravity up there is different and water doesn't flow as it should. Instead, they use liquid soap, water, and no-rinse shampoo. They first squeeze some liquid soap and water from pre-made water pouches onto their skin. Next, they open the no-rinse shampoo and add a little water to wash their hair. Towels are then used to wipe off the excess water, which is really precious in space. To make sure they recycle it, an airflow system quickly evaporates excess water. Gravity and weight shouldn't be confused. Astronauts on the space station do float, and you may sometimes hear that they are in the state of zero gravity. It's far from the truth, though, since gravity up there is about 90% of its value on our planet. But astronauts look and feel weightless, since weight is the force a certain object exerts on them back on Earth. Most creatures have evolved to sense and adapt to Earth's gravitational pull. In the sea, for instance, some fish have floating calcium carbonate deposits in their heads. Scientists call them ear stones, and they're pulled down by gravity. They act like a fish's internal compass. Now, plants have evolved to grow starch grains in the tips of their roots. They use this amazing feature to force their roots deep down into the soil. As little as we seem to understand it these days, we do need gravity for way more things than we can imagine. For instance, some bacteria become even more dangerous in space where there's little to no gravity. Salmonella, for example, the type of bacteria that is known to cause food poisoning, becomes 3 times nastier in the condition of microgravity. So you really gotta cook your chicken. Our own moon stays where it is because of the effects of gravity, too. If it weren't for this force, our satellite would have floated away by now. But it's held in place by Earth's gravitational pull. Objects with the biggest gravitational pulls in the universe are black holes. Thankfully, our planet is really far away from any of them. Nothing can escape the gravitational pull of a black hole, not even light itself. Similarly, gravity is different on each planet, and because of that, things weigh differently depending on which planet they're on. Take Earth, for example. An object that weighs 100 pounds here would only be 38 pounds on Mercury. But if you're planning on losing weight fast, try booking a trip to Pluto. Someone who weighs 150 pounds on Earth would weigh no more than 10 pounds on Pluto. The same person would weigh considerably more on Jupiter, which is the planet with the most powerful gravity. 150 pounds on Earth would turn into more than 354 pounds there. No thanks. Remember that experiment with watches ticking at different levels of elevation? It turns out that gravity isn't spread evenly on the surface of Earth. Why? because our planet isn't a perfect sphere. The mass of Earth isn't evenly distributed either. That's why you get variations in gravity in different locations. More so, gravity is weaker at the equator because of the centrifugal forces produced by the planet's rotation. Since we've always perceived gravity as a force, we seem to believe that it has somewhat of a suction motion. But it's not exactly true. Back in 1998, scientists were baffled to see that the expansion of the universe was speeding up. So they linked this to the repulsive gravity of mysterious dark energy. We now know that dark energy makes up for more than 60% of the mass energy of our whole universe. But since nobody knows what it actually is, we can only make assumptions. And one that's largely accepted is quantum theory, which seems to claim that gravity pushes rather than pulls things in. You got all that? I may need to watch this one again. This planet is often called the jewel of the solar system, probably because of how beautiful it is and how exotic it looks with colorful rings surrounding it. You've probably already guessed that I'm talking about Saturn, the second largest planet in the solar system. And the question is, can Saturn be a failed star? Now, a failed star is composed of gas, but it can't sustain nuclear fusion reactions in its core because it's not massive enough. This type of star is often referred to as a brown dwarf. Such space bodies are close in size to Jupiter, the largest planet in our solar system, but brown dwarfs have a much greater mass. Unlike other stars, they don't emit a lot of visible light since they aren't large enough to fuse hydrogen, even though brown dwarfs can fuse deuterium with lithium. Failed stars were discovered around 60 years ago. Some of the first theoretical papers describing them were published in 1962. If we talk about the first time astronomers confirmed the existence of a brown dwarf, it happened in 1988 when they spotted a space object later called GD 165b. Despite having a lot of characteristics of a star itself, this celestial body was orbiting another star and didn't meet all the necessary requirements to get this title. That's why scientists started calling it a failed star. Seems kind of harsh now, doesn't it? Since that first discovery, astronomers have spotted more than 50 other brown dwarfs. And according to the latest estimates, there might be around 25 million failed stars in our galaxy alone. Because of the lack of visible light, brown dwarfs are very difficult to spot, so this number might be inaccurate. You think? The most typical reason why a star might fail is that it doesn't manage to gather enough material to start regular stellar fusion. Now back to Saturn. The answer to the question of whether this planet might be a failed star is no. Why? The main difference between a planet and a failed star is the way they form. Stars appear when dust and gas collapse in a primordial cloud. That's why they contain low amounts of metals. At the same time, planets have significantly less mass than stars. That's why they have much lower gravities. And one of the main reasons why Saturn isn't a failed star is that it didn't start its life with enough mass to get the status of a star. A brown dwarf accumulates its star material in a similar way a star does, rather than following the method planets use. Thanks to their high gravity, failed stars can easily hold on to relatively light elements, like helium and hydrogen. For Saturn to become a failed star, it would need to be 50 times its current mass. But even if the gas giant decided to go through with the plan of becoming a brown dwarf, there simply wouldn't be enough material orbiting the Sun for this to happen. Any of the gas giants in our solar system, Jupiter or Saturn, would need at least 10 to 15 times more material to grow into a failed star. Not something you'd normally aspire to. You see, the Sun contains around 99.86% of the mass of the entire solar system. So, even if you combined all other materials in our star system, it still wouldn't be enough to create a star, even a failed one. Brown dwarfs and regular stars have a lot in common. Both start their lives as giant balls of gas. Both have protostellar cores. all of them start nuclear reactions and produce a lot of heat. Many failed stars produce some light too, but it mostly lies in the infrared spectrum. Now, let's look at the differences between these kinds of stars. A regular star releases light and energy due to thermonuclear reactions going on in its core, converting hydrogen into lithium. But a failed star doesn't have the mass to achieve this. Plus, failed stars are much smaller than regular stars, which generally possess more than 80 times the mass of Jupiter. A regular star normally has a gravitational pull strong enough to form a solar system with planets orbiting around it. As for brown dwarfs, they often orbit other stars. There's only one known failed star with a planet orbiting it. And I'm curious, why did scientists call it a failed star? Seems sort of academically judgmental to me. Did it get an F on some exam? How about other labels? Disappointing star or came up short star? But I digress. Okay then, how about Jupiter? After all, this gas giant is larger than Saturn. In fact, it's the largest planet in the solar system. Plus, this planet and the Sun are basically made of the same stuff. Both are mostly composed of hydrogen and helium with traces of other chemicals and elements. But the Sun is over 1,000 times the mass of Jupiter. If you place these two space bodies side by side, the gas giant would look tiny next to our star. So, what makeover would Jupiter need to undergo to turn into a star? If it wanted to be as large as our Sun, it would have to increase its mass by a factor of over 1,000. On the other hand, the Sun isn't the smallest or least massive star out there. There are red dwarfs, stars with the lowest mass. The smallest of them can be a mere 7.5% of the mass of the Sun. So, if Jupiter was striving to be called a star, it would be much more realistic for it to become a red dwarf. In this case, it would have to increase its mass by a factor of 80 or so. Interestingly, there's a tiny star in the Milky Way galaxy which is smaller than Jupiter. This is a red dwarf about 36,660 miles across that lies 600 light-years away from Earth. It makes the red dwarf one of the smallest known stars capable of supporting hydrogen fusion. Okay, we figured out that neither Saturn nor Jupiter can be called a failed star. But what if these two gas giants collided? Would they merge into one gas giant, which would then turn into a brown dwarf? Of course, at the moment, we're unlikely to see Jupiter and Saturn collide, which is a good thing. But let's speak about a hypothetical situation and its consequences. So, some time ago, scientists were sure that Saturn and Jupiter played similar games. At some point in the past, both planets reached the stage where they needed to vacuum up tremendous amounts of material in a relatively short period of time. But apparently, Jupiter got luckier in the process. Still, according to some studies, Saturn never had a running chance. You see, the critical threshold where a planet can gain a huge amount of hydrogen and helium is about 100 times the mass of our planet. And Jupiter indeed easily beats it, which might mean that it managed to acquire the lion's share of material in the outer solar system before the Sun blew it away. Uranus and Neptune turned out to be far too small to take part in this race for power. As for Saturn, it's right in the transition zone. Had it been a bit bigger, it could have probably competed with Jupiter for the title of the largest planet in the solar system. But instead of fighting its main competitor, Saturn got stuck. It grew large enough to attract a significant amount of hydrogen and helium with the help of its gravitational pull. But it wasn't enough to kickstart the process of nuclear fusion and get going. It means that, despite all the similarities they share, Jupiter and Saturn evolved along totally different tracks. And if these two planets collided, they wouldn't merge into one planet, let alone a star. If it was a head-on collision, the planets would destroy each other. Their gas envelopes would be eliminated, and the remains of their solid cores would be catapulted into the vacuum of the cosmos. But if the collision happened at an angle, the planets would probably survive it. But in both cases, the planets would lose a massive portion of their material. In one more collision scenario, the gas giants would simply slide across each other at an oblique angle. It would result in a change in their shapes, but wouldn't alter the composition or mass of the planets. Can we call that a failed collision? How disappointing.
Is the Force with you, or do you want to live long and prosper? The answer to this question reveals if you're a Star Wars fan or if you like Star Trek more. Ever since the franchises first appeared in the second half of the 20th century, they've been competing for fans all over the globe. People still confuse the two, so it's good to know what they have in common and which aspects they completely differ. Let's start with the genre. It might seem logical that all TV series and movies that deal with space travel can be categorized as science fiction. But that's not the case. Star Wars falls within the science fantasy genre. All the worlds on distant planets and characters are not based on human science. They are pure fantasy. Take, for example, the Force. It is universal energy that is part of all living things. It allows the movie's protagonist to move objects and control the minds of others. This is the famous scene when Yoda teaches Luke how to use the Force, but he fails at first. We would call this telekinesis. This isn't real science, it's best described as theatrical magic. Star Trek, on the other hand, has a more scientific approach to the exploration of space. The show is classified as science fiction. It deals with technological concepts that might become reality one day. For instance, the characters use communication devices. They also have the ability to triangulate an object or a person. Back in the 1960s, when the show first aired, it all seemed like science fiction to the viewers. Just a decade later, the first mobile phone appeared. Today, we all have smartphones that contain GPS maps. In a way, Star Trek screenwriters predicted the future. We might have to wait some time before teleportation becomes a thing, though. One of the most exciting segments of both franchises is space travel. Their spacecraft whiz across entire galaxies in seconds. In Star Trek, the USS Enterprise explores the universe traveling at various warp speeds. At Warp 8, it covers the distance from Earth to Alpha Centauri in about a day and a half. This is the nearest star system to our home planet. With the technology we have right now, it would take us 6,000 years to reach it. In Star Wars, spaceships are equally fast. At the end of the movie The Empire Strikes Back, Han Solo propels his Millennium Falcon into hyperspace.
To do this, his flying vessel has to travel faster than the speed of light.
So, commuting across the vast expanses of the universe is not a problem in Star Trek and Star Wars. But both franchises feature some small world syndrome. All the characters seem to know each other, or they're related in some way. Also, the protagonists appear to bump into the same villains over and over. In 1967, the associate producer of Star Trek couldn't believe what one of the series' writers suggested. He wanted Captain Kirk to encounter a Klingon commander that appeared in the previous season of the show. I mean, what are the odds that the two run into each other again? The universe is endless, but so is the screenwriter's urge to shrink the fantasy world of both franchises. The duo has promoted another cliché. Have you noticed that while lasers whiz by, the main protagonist is always the best marksperson? Stormtroopers from Star Wars have cool-looking white protection suits, but they easily go down when the good guys take aim at them. Encounters with new species in Star Trek can also get out of hand. But in the end, Captain Kirk and his Starfleet crew always come on top. With several notable exceptions, fans still can't get over the fact that the lovable character of Data doesn't appear anymore. This perfectly reflects how protagonists constantly face dilemmas as they explore the universe. Should we help that planet or not? This makes the plot of Star Trek episodes more intricate than the manner Star Wars movies play out. A group of people seeks liberty, but the no-good Empire doesn't want them to be free. Without this friction, the movies would be left without a plausible plot. The film's authors made it obvious who the good guys were. They wield green lightsabers, as opposed to the red ones bad guys have. Anyone in the audience who ever crossed a traffic light will know who to support on the big screen, and the antagonists are on the dark side. It doesn't get more obvious than that. You're thinking about Darth Vader, aren't you? He's perhaps the most memorable character in the whole franchise, and it's not like he's the only one. There's also Luke Skywalker, his son. I hope I'm not spoiling the movie for you. After all, the iconic hand scene is over 40 years old. Other memorable characters include Han Solo, Obi-Wan Kenobi, Yoda, Princess Leia, R2-D2, Chewbacca. The list goes on. Over the decades, Star Trek also introduced iconic characters: Captain Kirk, Captain Picard, Mr. Spock, and so on. When it comes to creatures they encounter on space travels, Klingons are the most memorable bunch. These humanoids have a shifting relationship with the Federation. In the beginning, the Klingons were their opponents, but over time, the two have learned to work together. Fans love to dress like this race at gatherings. They even wrote a dictionary of the Klingon language and started talking in it. Hey, you can learn to speak it on Duolingo. Despite their popularity, the Klingons never receive a show of their own. Because of their way of life, the Mandalorians from Star Wars are the most similar to Klingons. They got their own TV series in 2019, and it's all thanks to one character, Boba Fett. His well-designed helmet and the jetpack on his back made him the fans' instant favorite. The final linchpin between the two franchises is not a fictional character. J.J. Abrams is very much real. He's an American filmmaker who produced 2 Star Trek movies and 2 Star Wars movies. Trekkies believed he made their beloved franchise look like Star Wars, and that's a big no-no. Star Wars enthusiasts thought he just copied the plot from previous movies. They didn't think Abrams was creative enough. Whatever the case, you have to make a choice which franchise you like better, like Quentin Tarantino did. The lauded American director prefers Star Trek to Star Wars, and it's not because of the show's plot, but rather one man, William Shatner. The Canadian actor won over TV audiences by playing the role of Captain James T. Kirk. For Tarantino, this was one of the greatest performances in the history of episodic television. The man loved Shatner's acting skills so much that he even planned to shoot a Star Trek movie. The script was there, but he never got around to the actual filming. Just imagine, it would have been Pulp Fiction in outer space. This doesn't mean that other directors didn't film Star Trek movies. So far, there are 13 of them. That's 2 more than Star Wars movies. Here comes the odd part. Star Trek started off as a TV series, but there are 6 of them in total. Compare that to 8 Star Wars TV series. Both franchises heavily influenced pop culture. They had numerous spin-offs, books, non-canon TV movies, video games, comics, and theme parks. Scientists named 17 animal species after Star Wars characters. There is a moth called Wakia Chewbacca fluttering its wings somewhere in Mexico. In 1976, NASA named one of its space shuttles Enterprise after the fictional flagship from Star Trek. Its original proposed name was Constitution. Not nearly as cool, don't you agree? 2023 was going to be the year of the final showdown between the franchises. Star Trek IV and Star Wars Rogue Squadron were set to come out on the 22nd of December, 2023. That would be the first time in history that the release dates of both franchises match to a day. But there are production issues for both movies, so this is unlikely to happen. Imagine the universe as a gigantic, elastic balloon that's steadily being inflated. That's what dark energy seems to be doing, forcing galaxies further apart. Could this force lead to the end of the universe? Some scientists do think so, and they've named this potential event the Big Rip. It's challenging to study dark energy, even though it's one of the most fascinating aspects of our cosmos. That's because its only visible effect is this gentle stretching of space. On any smaller scale, it's virtually undetectable. Compared to dark energy, studying dark matter feels like a walk in the park. Even though it's just as invisible, dark matter leaves clear evidence of its existence. It latches onto galaxies and galaxy clusters, bending light and altering gravity. Dark energy, on the flip side, just expands. Nonetheless, scientists have found ways to examine it, mostly by observing the universe's expansion. As we peer into the distance, we are, in fact, peering back in time, tracing the universe's evolution. Dark energy could also bring about the end of the universe in a massive, catastrophic event. Imagine watching helplessly as reality itself tears apart with no hope of escape. Frighteningly, it's not some far-fetched scenario. The available data does not eliminate the possibility of a big rip. Is dark energy a force that keeps inflating the universe, or is it more like a separator? If two galaxies are far away from each other, they're driven further apart, leading to increasing cosmic isolation. But anything that's already a strong structure stays intact, immune to this divisive force. Why doesn't it mess things up, you ask? Well, it's because dark energy remains consistent. As space grows bigger, the density of dark energy remains steady. Imagine drawing a circle anywhere in space, taking note of the amount of dark energy there. Do it again after 1 billion years, and guess what? The amount of dark energy inside your circle won't change, even though space itself has expanded. That is, unless, of course, dark energy has a trick up its sleeve and proves to be more potent than a cosmological constant. All we know for sure is that it's something that drives the universe to expand more rapidly. Or to put it another way, it creates negative pressure. Now, negative pressure might sound odd. Pressure is usually seen as an outward force, right? But in the universe, it behaves differently. Pressure is a type of energy, like mass, that attracts rather than repels. All these calculations are what makes the Big Rip picture a slow, unraveling movie. The first objects affected are the most massive, loosely bound structures, like giant clusters of galaxies. Their gravitational pull will start weakening, causing them to drift away into the growing cosmic voids. Next, we'd notice stars on the outskirts of our galaxy not following their usual paths, but instead drifting away, like party guests saying their goodbyes. The night sky would then start to dim as our Milky Way would gradually evaporate. The disaster would just accelerate from there. The orbits of the planet would begin to shift, spiraling outward. Just months before the end, after we've lost the outer planets, Earth would drift away from the Sun and the Moon from Earth. We would plunge into the darkness alone. The stillness of solitude won't last, however. Any remaining structure would be destroyed because of the expanding space. The Earth's atmosphere would start to thin. Gravitational shifts would cause chaotic tectonic movements. In the final hours, Earth would fall apart. Beyond this point, the destruction would continue unseen. Nuclei, the ultra-dense cores within atoms, would disintegrate next. Black holes' dense cores would get obliterated. In the last instance, space itself would just rip apart. Bad as it may sound, we may never rule out the threat of a big rip. However, it might take so long that all cosmic structures will have decayed before it happens. A rough calculation suggests the earliest big rip could be in about 200 billion years. Technically, the Sun still has about 5 billion years before it fades away naturally. So by the time this event might happen, our solar system would have long been gone. Nonetheless, given the possible implications, scientists are placing a high priority on understanding the Big Rip. Let's be optimistic though. I mean, if we look at the universe's history, we should consider ourselves lucky. We're in what cosmologists refer to as the luminiferous era. It means that right now the universe is still pretty busy producing new stars, and we know how important these celestial bodies are for maintaining life as we know it. However, the golden age of star formation was about 10 billion years ago. Ever since that peak, the rate of creating new stars has been on the decline. Now, why is the universe taking this early retirement? It's not because it's lazy or tired. In fact, it's exactly because we're living in this expanding universe. For a new star to appear, a bunch of matter needs to be squeezed into a relatively small space. It's like trying to stuff all your clothes into a very, very small suitcase. As the universe expands, the matter is getting spread out, leading to less and less room in that suitcase for creating new stars. The Big Freeze, another theory related to the end of the universe, looks at this scenario. Stars will become endangered and then extinct species. This period of star decline is what astronomers like to call the degenerate era. It's estimated to start about 100 trillion years into the future. What'll be left in the night sky at that point? Only the hardened workers of the universe, white dwarfs, neutron stars, and black holes. White dwarfs and neutron stars, the remnants of medium and large stars that have exhausted their nuclear fuel, will eventually cool off and transform into black dwarfs. These black dwarfs are like invisible cosmic spirits, just hanging around without doing much, inert and unseen. Other neutron stars, too heavy for their own good, will stumble under their weight and collapse into black holes. Further into the future, the universe will become a black holes-only party. But even these cosmic weirdos can't cheat time forever. Black holes can fade away too. In fact, this idea of fading black holes came from a brilliant mind you might have heard of, Stephen Hawking. He suggested that black holes slowly shed energy in the form of radiation until they shrivel up like raisins and evaporate completely. Eventually, every single black hole will have evaporated. We'll be left with a universe in its twilight years, settling into its final age, aptly named the Dark Era. At this point, both light and matter will be nothing but distant memories. And then, well, nothing. If this Big Freeze theory is correct, the universe will just remain in a quiet, dark state stretching into an eternity where nothing else ever happens. Most of these theories seem to rely on the fact that the universe is expanding. But what exactly is it expanding into? We can't help but wonder if there's something else beyond our universe. Right now, this question is one for which physics doesn't quite have an answer for. We don't have enough facts. One suggestion is that time and space came to be with the Big Bang. That happened around 14 billion years ago, so logically there's nothing beyond the universe. However, a huge chunk of the universe is way out of our sight, existing beyond the part we can observe, which is about 90 billion light-years in diameter. Because everything's pretty much the same wherever you look in the universe, we can presume that the bits we can't see would look pretty much like the parts we can. But that's just an assumption. Now, if the universe is infinite, there's nothing beyond it, right? I mean, that's just what infinite means. On the other hand, if it's finite and growing, you'd start to wonder if there's a boundary or an edge, like a universal cliff that separates our universe from whatever is beyond it. It gets even more complicated when you realize the universe has at least 4 dimensions, 3 for space and 1 for time. And it's pretty much impossible for us to picture what that might look like.
Now, we all know that all planets are round. There are no square ones so far, and that's because of gravity. Well, roundish at least, as not all of the planets have perfect proportions. But did you ever wonder about the shape of the universe itself? Is it also round because of the same forces? Well, not really. Based on what information we have so far, the universe is actually flat? According to the principles of general relativity, space has the ability to curve. This opens the door for the universe to have 3 potential shapes: a flat plane like a sheet of paper, a closed sphere like a bowl, or an open saddle-like curve. This isn't just a matter of academic interest, you know. The universe's shape has direct consequences on its ultimate destiny. One cosmologist from Princeton University explained it beautifully. The shape of the universe is a kind of map to its past and a predictor of its future. The questions of whether the universe will keep expanding forever or collapse at some point, and if it's finite or infinite, all circle back to the question of its shape. Now, to wrap your head around this cosmic question, you need to understand 2 key elements. the density of the universe and its rate of expansion. Let's dig into this a little. Around 68% of the universe is made up of dark energy, while 27% is dark matter. The rest, which is normal matter, if you'd like, makes up the stars, planets, and other cosmic bodies we're familiar with. When we talk about the density of the universe, we're referring to the quantity of normal matter packed into a given volume of space. Now, if the universe is denser, it also has more gravity. In this case, the gravitational pull can overcome the force of expansion, so the universe curls up into a sphere. This shape is known as the closed model, where the universe ends up looking like a gigantic cosmic ball. Imagine a world that's finite but without boundaries, a contradiction for sure. In this model, an adventurous explorer could travel forever through space, never bumping into a wall or falling over an edge. Alternatively, if the density of the universe is low and not enough to halt the expansion, then space distorts in the opposite direction. This results in an open universe with negative curvature that resembles a saddle, like on a horse. Despite these two potential scenarios, most scientists agree that the density of the universe is just right, which means it expands proportionally without curving. But what does it mean if the universe is flat? It doesn't mean we're living in an infinite sheet of paper. To understand it, consider these analogies. Imagine you're in a square room, walk 10 steps to the next corner, make a 90-degree turn, walk another 10 steps, and repeat this process twice more. You end up back at your starting point, completing a square. Add another dimension to this geometry, since we're not 2D creatures, and whoopee, you have a flat universe. This analogy wouldn't hold up in a curved space. If you have a terrestrial globe at home, you might find it easier to understand this next experiment. Start by placing your finger at the Earth's equator, then trace a line to the North Pole, make a 90-degree turn, and return to the equator. Make one more 90-degree turn and walk back to your starting point. This journey only needed 3 turns, unlike the 4 turns in the flat universe scenario. Still struggling to understand? Here's another way to picture it. In a flat universe, 2 rockets traveling side by side will always remain parallel. This is in contrast to a closed universe, where the rockets will travel along the curve of space and eventually meet where they started. In an open universe with negative curvature, the rockets will gradually drift apart and never cross paths again. So, is there a cosmological crisis at hand? It seems the answer to the shape of our universe is encoded in the cosmic microwave background, also named CMB, which is like the universe's fossil record. Over the past few decades, scientists have measured temperature fluctuations in the CMB to find almost no curvature, indicating a flat universe. Now, the concept of a flat universe is crucial to the standard cosmological model. However, in late 2019, scientists from a university in Rome published a paper arguing that current CMB measurements actually indicate we're really living in a closed universe. How did they figure this out? Well, they looked at how light behaves in the universe. Specifically, they analyzed how light bends because of the gravitational force of matter in its path. Either way, apart from this finding, there's nothing else that would suggest we're living in a closed universe. Most scientists believe this recent discovery is nothing more than a statistical anomaly. But if the closed universe theory turns out to be right, it would shift decades of astronomical findings. If the universe is indeed curved, it must be so large that the observable 93 billion light-years aren't enough to reveal its curvature. It could be similar to standing in a fog, only able to see a small, flat patch of land. Yet somewhere out of sight, the horizon reveals that we live on a sphere. As we continue to probe the cosmos, we might find that the apparent flatness of our universe is just a small part of a much larger, curved cosmos. Its shape is just one of the many things we've yet to figure out about the universe. We can't quite put our finger on why the universe is even here, for instance. We do have some theories, but scientists are yet to be sure. It could be that the universe is like a pop-up, materializing out of an unstable nowhere land. Imagine the emptiest emptiness you can think of, suddenly churning out matter and energy in equal and opposite amounts that tally up to zero. For most of us, it's hard to picture that process. If we follow this theory, who's to say there's only one universe? We might be just one of an enormous collection, a so-called multiverse. For now, we'll just have to wait for the next wave of cosmic measurements to refine our theories, and for scientists to come up with hypotheses that aren't just mathematically pretty, but actually testable. Also, how could we possibly know all the secrets of the universe if we don't completely understand our own biology yet? I mean, if we did, we could, theoretically, solve all of our health problems, right? We might even be able to play around with our DNA, like this molecular Lego, and give ourselves naturally purple hair or red fingernails. Well, time for a reality check, as we're still struggling with this one too. Here's a great example: our microbiome. Our bodies, home to 10 trillion human cells, are also an active city for 100 trillion microbial cells. That's a couple of pounds of bacteria and other microbes, which we absolutely can't do without. They've set up shop in our bellies, lungs, noses, and every other hidden nook and cranny. We're like luxurious cruise ships for these tiny microbial tourists, and we still don't fully understand the implications of this symbiotic relationship. There are still a lot of things we don't know about planet Earth either. We've only ever dipped our toes into Earth's crust, never venturing more than a few miles deep. Everything else is our best guess, from remote sensing and smart physics. Believe it or not, it took us an embarrassingly long time to accept that the Earth's crust is constantly shifting, like Jenga pieces. We only warmed up to plate tectonics in the mid-20th century. We're also still trying to figure out precisely how the planet's inner engine works, and how the swirling, conducting materials in the outer core create our protective magnetic field. Plus, with 4.5 billion years of geological chaos, we're sometimes better off studying meteorites or the surfaces of other celestial bodies for clues about our planet's history. Even our faithful companion, the Moon, is a bit of a mystery. Was it born from a colossal collision or some other event? We're still not sure. But hey, the fact that we still have a lot to learn is what makes life interesting, isn't it? That, and the thrill of actually finding an empty parking spot in San Francisco, or maybe even your city. Are we really by ourselves in the universe? It's a daunting question that's been haunting us for centuries. No wonder scientists have tried to come up with all sorts of ideas as to why. One of the strangest theories concerning our lack of contact with other life forms is named the dark forest theory. Let's start small, well, sort of. We'll focus on our Milky Way, for now, to better understand this theory. Our cosmic neighborhood is a galactic wonderland, sprinkled with 200 billion twinkling stars and maybe around 100 billion planets. So let's get hypothetical for a moment and say a tiny part of those habitats hosts life. Further, out of those life-bearing planets, a few might have evolved into intelligent beings. Given that, you'd think we'd be knee-deep in weird-looking neighbors, some of whom might be actively trying to find us or might just be out there, waiting to be discovered. Now, let's put a little science into this science fiction scenario. We have something called the Drake equation, which is a kind of universal roll call that estimates how many smart civilizations could pop up in our galaxy. You can think of this equation as the super smart roadmap. By playing around with a few important factors, the equation hints that there should be around 20 civilizations just in our galactic backyard. So why haven't we stumbled upon any yet? This theory isn't an easy task. It's a mixed bag of multiple variables, like the average number of planets per solar system that could potentially host life, or the rate at which stars suitable for intelligent life are formed. A tricky part here is that astronomers have yet to solidify the exact values of these variables, which means our calculations are just approximations for now. But back to the Milky Way, shall we? Feed in our hypothetical assumptions, crunch the numbers, and you get at least 20 civilizations. Yet somehow, our cosmic switchboard remains weirdly silent. How come? This radio silence has its own name, too, the Fermi paradox, named after the guy who first thought, "Hey, where is everybody?" over 50 years ago. Since then, we've had a lot of different theories trying to solve this mystery, all tinkering with different aspects of the Drake equation. Some folks think the appearance of life is a rare event. Others think that getting from bacteria to advanced beings is the tricky part. Yet, some reckon that civilizations might either wipe themselves out after a short lifespan or never even get to invent something they could communicate with. But there's one theory that tops all others in its creepiness: the dark forest theory. According to it, the universe is a huge cosmic version of a haunted forest. And other types of creatures are out there, playing a game of hide and seek. They're intentionally keeping silent. Why? Well, the dark forest theory was best explained in a sci-fi novel, and the rationale goes something like this. For starters, every life form wants to stay alive. I'll buy that. If we go with that assumption, it's impossible to be sure whether other life forms might harm you if they get the chance. So, the safest bet is to take them out before they find the right time to do the same to you. Frankly speaking, it's the universe's version of the survival of the fittest. In this scenario, making contact with others becomes the most dangerous game, as it could lead to your location being traced and you being wiped out. How human. This results in everyone keeping quiet, a kind of universal shush, where every civilization tries to hide in utter cosmic silence. But hey, is this just an idea good for a thrilling novel, or does it have some real-world implications? Well, the theory was suggested by scientist David Brin as a possible explanation for the lack of radio evidence for non-Earth-like life. He went as far as imagining it would be robots that would do the dirty work of wiping out civilizations. But how realistic is this theory anyway? Well, it doesn't require us to assume a lot of stuff about the behavior of all foreign civilizations. Just one advanced race behaving this way could explain our observed reality. And it might explain why we've not picked up any advanced radio chatter despite a century of eavesdropping. It's possible that other creatures like us are too terrified of being noticed and have gone radio silent on purpose. But, and it's a big but, like mine, it does base itself on the notion that other species share our level of risk aversion and logic, or that there's a rogue civilization out there, picking off anyone they perceive as a threat. And that's a pretty significant assumption. If that doesn't sound creepy, this next piece of information certainly will. For about a century now, we've been shouting our existence into the cosmos. If this theory proves to be correct, every other civilization within 100 light-years of us might be getting our signals and knowing exactly where we are. And if we have reasons to hide from them, as suggested by some like Stephen Hawking, we might already be in trouble. But what if this theory isn't true? What if, sooner than we'd like to imagine, weird galactic creatures will indeed try to reach us? The truth is, most of us wouldn't even know what to do. Hey, let's not get over ourselves. In fact, some scientists are tackling this issue head-on. For the first time since the 1980s, specialists are trying to cook up a how-to guide for when we inevitably bump into cosmic neighbors. For instance, some researchers believe we've got to do more than just worry about how these life forms could shake up our world. If they send any type of radio signals down here, we've got to think about our reply. What are we going to say? Hey, we're humans. Nice to meet you. Absolutely not. We've got to do better than that. See, the only plan we've had till now came from a rough blueprint dating from 1989. This guide is a bit wishy-washy on what to do when the entire world gets the outer worldly text. Mostly it says, hey, let's share the news with everyone. But then what? If we confirm it's legit, officials will need to ask the United Nations for advice. But hey, does the United Nations even have a plan? Maybe, who knows? We've been doing loads of space exploring lately. Some say we've stumbled upon water on Mars. Others are sure we've spotted some planets that could be twins to Earth. So, the idea of finding life elsewhere isn't that far-fetched. But even after 100 years of trying to chat with cosmic beings, it's still a one-sided conversation. This new protocol isn't just about chatting up outsiders. It's also going to act as our cosmic voicemail, checking messages from outer space. It aims not just to decode the external lingo. It's also planning to figure out what these messages could mean for us. The plan is also to draft reports about how different policies could impact us and set up guidelines on how to respond to these space texts. So, will we ever get a message from our cosmic mates? Only time will tell. But what we do know is that we just can't wing it. We can't be caught off guard and start a planet-wide frenzy when we get that otherworldly WhatsApp. We gotta have a plan, and we gotta have it ready for when we're face-to-face with the real deal. I mean, we've come across a lot of potential such sightings, but none of them proved to be genuine. On that note, U.S. authorities checked over 100 cases of weird stuff going on in the skies. I'll spare you the details, but not one green creature was ever found. More like drones and similar stuff floating around. So, as we stand on the cusp of this potentially game-changing event, we must strive to be prepared. Whether our intergalactic neighbors drop us a text tomorrow or centuries from now, we need a plan. After all, this could change everything we know about our universe and our place within it.